Alright, we're going to talk about extrasolar planets. Extrasolar planets are planets around other stars, other than the sun. And everybody suspected from way back that there were planets around other stars, we just couldn't see them. The stars are so far away, the planets are so tiny, it was impossible to detect. It wasn't until about the mid to late 90s and then through the 2000s that we finally started discovering extrasolar planets. And as of now, there are over 4,000 known extrasolar planets. And there's several thousand more what we call candidate ones where we think there are, but there's not enough follow-up work to confirm that they're actual planets. Now let's talk about there's three ways of detecting these extrasolar planets. One is the wobble of the star, which I'll talk about in a sec, the transit method, which detects most of the extrasolar, and direct imaging, which doesn't happen very often, but there are a few where we can actually see the planet. So the wobble of the star, the idea is as the planet orbits around the star actually has to make an orbit too. Essentially, both of them orbit around the center of gravity of the system. It's kind of like if you're on a teeter-totter where you balance is determined by how much mass the two objects have. Okay, in this case, the star has a lot more mass than the planet, so the center of gravity is very close to the star, but the star makes a little loop, and we can measure that motion of the star, and by measuring the motion of the star, we can determine that there must be a planet there. How we measure it is when the star is coming towards us, the light coming from the star gets shifted to the blue, or what we call blue shifted. The wavelengths get shorter. When this object is going away from us, the light is red shifted, or the wavelengths get longer. Remember, red light is longer wavelength than blue light. And so all we do is we look for this, and the light of the star over time will be red shifted, then it'll go to be normal, then it'll be blue shifted, then it'll get red shifted again, and we watch how long that takes, and how long that takes tells us the period of the planet going around. By the period of the planet, we can figure out how far away it is. By how much it shifts, we can figure out the mass of the planet. So we can learn a whole lot when we find these. The problem is it's really skewed towards the high mass planets, because this is data. This is actual data from the Keck telescope. And you see this is complicated here. There's kind of a wave like this, and then there's a really fast wave. Those are two different planets that they studied, and they had to study it over like 5 or 6 years to get enough data to actually figure out what's going on here. And this is what they figured out, that there were two planets orbiting this star. One here that has 0.6 the mass times Jupiter. This is twice the mass of Jupiter. So these are very massive planets. Bigger than the planets we see that are that close. Because remember, close to our sun, we have Mercury, which is very tiny. It's about the size of the moon. And then Venus and Earth, and we're much, much smaller than the mass of Jupiter. And so these are very close, because their orbital period is 30 and 61 days. Even Mercury and our planet, Mercury would be out here because it takes 88 days to go around. So we have two very large planets very close to the star, which makes it easy to detect. Completely different than our solar system. In our solar system, all the rocky planets are close to the star, and all the large, what we call the gas giants, are further away. In this situation, in this system, that is not the case at all. The transit method is the method that's most used to detect these planets. And what you see is what happens if it lines up. So it's a planet orbiting the star. If it lines up just right so the planet actually passes in front of the star, then while it's passing in front of the star, it's blocking out some of the light. As it blocks out the light, then we can see, or what we do is we watch that star, and we watch for the star's brightness to change. So you put your telescope on the star, and you just watch it all night long, and you see for any change in brightness. If the brightness all of a sudden dips and then comes out again when it gets to the other side, that means a planet passed in front of it. And that's how they find these planets, is they just look at stars for many, many nights, sometimes years in a row, and they look for any dips that happen to occur. Now the challenge is Jupiter ones are much easier to find because the Jupiter is about 1% the area of the sun, so it blocks out about 1% of the light. Where ones like Venus or Earth size, the planet is so tiny compared to it, it's only blocking out about 1/10,000th the light of the sun. Well, usually this is very hard to measure, especially from the ground. You have to be up in space to measure this kind of accuracy. These you can measure from the ground. In fact, we do it at our observatory here at Commerce, Texas. This shows what a transit looks like. So this is the brightness of the star, and then when it hits here, the planet passes in front of the star and it blocks the light, and then this is when the planet comes out the other side and the brightness of the star goes back to normal. By the shape of this, we can tell exactly how big the planet is, how far away it is, what its mass is. And so we can learn a lot about it, and that's how they find most exoplanets nowadays. Now the Kepler mission, which was launched in 2008, was specifically launched into space to look for these planets around other stars. It looked for a position in the Milky Way where it could see about 1 million stars, and it would take pictures of these 1 million stars, and it took pictures of the same stars for like 3 straight years in a row. But because it did that, remember they have to be lined up perfectly edge on so the planet passes in front. Most planets are going to orbit and not cross in front of the star. But out of 1 million stars, that only happens about 1 every 1,000 or 10,000 times. That still leaves you several thousand stars out of those million that have planets that we can detect. The other way, and this is futuristic because it doesn't exist yet, but the plan is to put telescopes up in space, a whole slew of telescopes that are all connected together. They're either connected together by light, by laser transmissions, or they actually are tethered together through some kind of wiring system. But what they do, is they should be able to directly take images of planets. The only ones we have now are stars where the planets are very close to us, or the star is very close to us, so it is possible to see the planet. I'll show you some of the few of them we have. Like here is one. So this is kind of a crazy picture, but this was a picture taken where they blocked out the light of the star. This is just star left over from the star because the star was actually so bright, normally you couldn't see the planet. But they blocked that out, did a whole bunch of Photoshop techniques so it would eliminate the brightness of the star, and they found that, boom, right there is a planet. And so that's one of the few direct imagings of a planet we have. Here is another one. This is a planet orbiting a star. And here is a third one. This one actually has two. So this big blob here is the blocking out of the light from this star. And these are the planets orbiting that star. So that's very, very accurate. And very few. This only works for stars that are very, very close to the Earth that we can actually see the planets directly. Alright, so what do we know about the planets? As of now, there's some 4,000. This was in 2019, there's 4,016. I think we're going to know about like 4,200 or something now. It keeps going up. In fact, it's hard to keep track of. There's so many of them being found. But what we care about are the ones that are the most interesting. In fact, what we care about in this one is the ones that might possibly have life. And remember, we're looking for life like we know it on Earth. And so what we want is we want them to be at the exact distance where liquid water can form from that star. So it depends on the star, how hot the star is, or how cool the star is. If it's a star like our sun, then we need to be in about a 1 to 1.7 AU distance. Right in this direct region right here are the ones at the right distance where liquid water can exist. You get too close up here, these are way too hot. You get out here, they're frozen. So we've got to have that magic point. And this shows it here. So these are all planets out here that have been found, all right? Now, you look here, this is distances from their star, okay, and this is planetary radius. So the Earth here has a radius of 1. We're at about 93 million miles, so we would be out here. This is the region you want to be. These in here are too hot. So it's not as likely to have life on them because liquid water has a hard time existing because it's so hot, it's in a vapor form continuously. Alright, so this is another way of looking at it here. We're looking at temperature. Now this is in Kelvin versus orbital distance. So the Earth, we're here and our temperature is about 300 Kelvin, right in this region right here. So any in here are very likely to be very similar Earth-like and to be having the right temperature. So this is another way. These are Kepler ones again, but these Kepler ones, this is a diagram showing those energy received by the planet, okay? And this is surface temperature. This is a good representation. Can you see the green area in here, especially the lighter green? That's what we call the Goldilocks zone. That's the magic spot where water can exist in a liquid form. Notice for our solar system, you see here's Earth and here's Mars. Venus is over here. Both Earth and Mars are in the right region of this Goldilocks zone so water can exist on the surface. Mars was in the back of it, Earth in the front. We're in the danger of actually becoming too hot. We're on the front edge of this. And that's why everybody worries about global warming, because global warming could push us off to this edge where we actually just get too hot. If it runs away and gets really bad. That's what happened to Venus. Venus is just too hot. Our solar system would have 2 planets with life if we had flipped Mars and Venus around. Because Venus is about the same size as Earth, but the problem is it's in here where it's too hot. Mars is too tiny, so it lost its atmosphere, so it got too cold. But if we flip those around, if Venus was here, we would probably have life on Venus and life on Earth. All right, but you see all the blue ones and the white ones here? These are candidates or confirmed ones. These are candidate ones, and these are new ones. These are the ones that we're most interested in because those seem to have life-like conditions. All right. It's also possible you could have life around something like on a moon of a planet that's a Jupiter-sized planet. So even though we find a Jupiter-sized planet, it could have life on a moon, but there's no way for it. We can barely detect a planet. There's no way we can detect a moon around a planet around a distant star at this point. All right, and this is just an artist's rendition of the probably best ones, the best chances for being Earth-like and being possible to have life on, or potentially habitable exoplanets. And these are ranked in distance. So 4.2 light years, that's the closest star to us. That's part of the Alpha Centauri system, this Proxima Centauri, out to about 1,200 light years. So those are the ones that are the most interesting. Of the 4,000, these are the ones that are most likely to be very much Earth-like. And we think if it's Earth-like, it's probably going to have life on it. All right, that's it for the exoplanets.